This is Mastering Physics, Chapter 13, Number 70, and the problem says we have the Solar Heliospheric Observatory parked in an orbit slightly inside the Earth's orbit, as shown in the figure. The satellite's period in this orbit is exactly 1 year, so it remains fixed relative to the Earth. At this point, called a Lagrange point, the light from the sun is never blocked by the Earth, yet the satellite remains nearby, so the data are easily transmitted to Earth. What is SOHO's distance from the Earth? The hint is to use the binomial approximation. SOHO's distance from the Earth is very small compared to the Earth's distance from the sun. So where to start? Well, draw a diagram and label those relevant distances. So in our diagram, we've got the sun. We've labeled the orbital radius of the Earth about the sun. That's this distance. We also need to know the orbital radius of the satellite about the sun. Note it's a center-to-center distance. We'll call that little r. We also need to know what we're looking for, which is the distance, d, between the Earth and the satellite, which we've labeled. Another relevant feature is that there are two forces on the satellite. There's the force of the Earth, the attractive force of the Earth, pointed toward the Earth, smaller than the attractive force of the sun pointed toward the sun. That means that the net force, if you add those two forces, is pointed toward the sun. That's a centripetal force. That there is a force that keeps the satellite in its circular orbit, and that in this case is the net force, if you take the sum of these two forces. So let's do that. The net force is equal to the vector sum of those two forces. So the first force, the force of the sun, g times the mass of the sun times the mass of the satellite divided by the distance squared. So we label that r squared. And then we'll subtract. We'll take in the other direction g times the mass of the Earth times the mass of the satellite divided by d squared. That's the difference between the two forces, and we'll just call the force toward the Earth in the negative direction, in the opposite direction. We said that the net force was a centripetal force, so that means that those two forces sum up to the mass times the centripetal acceleration. In general, the centripetal acceleration is v squared over r. So we can fill in some details. Let's look at nv squared over r. Factor out n over r. V squared is going to be equal to the distance, 2 pi r, about one orbit divided by the orbital velocity, or rather the time, the period, the orbital period, which we were given. So the period of the satellite is the same as the period of the Earth, 1 year, as it turns out. And if we simplify that, that looks like m times 4 pi squared. Now you've got an r squared, but you also have an r in the denominator, so that just simplifies to r over the period squared. But we know from Kepler's law, Kepler's third law, that the period of the Earth squared is equal to 4 pi squared times the orbital radius of the Earth cubed over g times the mass of the sun. So now, if I take this expression and plug in for the period of the Earth, which is the same as the period of the satellite, I get m times 4 pi squared times r, and then divide. You've got a 4 pi squared. You've got the orbital radius of the Earth cubed over g times the mass of the sun. Now if we simplify, 4 pi squared goes away. You have g times the mass of the sun times the mass of the satellite you have r, and you have all of that divided by orbital radius of the Earth cubed. Now let's fill in for r. Remember our original diagram. If we call that r, that distance is the same as the orbital radius of the Earth minus d. So let's fill that detail in. G times the mass of the Sun times the mass of the satellite times the orbital radius of the Earth minus d. Divide all of that by the orbital radius of the Earth cubed. So if we write out the entire expression, because remember this piece here is just nv squared over r. The entire expression has to include these forces: g times the mass of the Sun times the mass of the satellite over little r squared minus g times the mass of the Earth times the mass of the satellite over d squared, and that's equal to g times the mass of the Sun times the mass of the satellite times the orbital radius of the Earth minus d over the orbital radius of the Earth cubed. And let's do one more thing. Let's fill in, instead of little r, let's fill in the orbital radius of the Earth minus d. So we take g, mass of the Sun, times the mass of the satellite over the orbital radius of the Earth minus d squared minus g times the mass of the Earth times the mass of the satellite over d squared equals g times the mass of the Sun times the mass of the satellite times the radius of the Earth minus d over the orbital radius of the Earth cubed. Now, what do you do with that? Well, you apply the binomial expansion. So that's what we'll do next in part 2.